So this is the lecture 5 that we have for this particular subject. And yesterday what we covered, that I'll go through within 30 seconds. What was the points that we covered is pre-processing, solver and post-processing. So these were the three phases of the CAE, that tools we use for analysis of any mechanical part. And this yesterday we discussed in brief, and in detail we are going to see that. But before going through in detail, these three, pre-processing, solver and post-processing, that we are going to see in the image form. You see here that if you can see the cursor, I'll make this somewhere else. Okay, so here this ellipse that you can see, where geometric modeling and this pre-processing, that is meshing and all, that is being shown in this particular envelope, and the solver is there here somewhere. Computer is going to use for solving that, and after solving you will get post processing like this. So here in the color form, what you are getting is actually the distribution of the parameter that you want as the outcome as a post processor. So that parameter from minimum to maximum is represented in some color, and these colors on this particular physical entity, on this model that you can see, is representing that particular amount there. If suppose I take the example of displacement, or if I take the example of deflection, then these colors are having some values of displacement, and therefore that color, at that color, that particular displacement will be there like this. We will understand that in detail, no doubt, in future. Here first unit is a summary of all syllabus that we are going to cover actually, right? So whatever the points that you are going to see now, that you are going to learn now, that you are going to study now, actually you are going to understand this in detail in coming units. And therefore when you will complete that all units, and again when you will go for learning first unit, you will find that first unit is very easier, because all these words, terminology and all that you have understood in brief as well as in details in the coming units. Therefore these terms will be familiar to you, although now it may be possible that it is not familiar to you, right? Okay, so for future, don't worry. Then going for the next slide, and the next slide is here. I think we have slide option also, right? Okay, so pre-processing slide is there. So as I said, we will go through these three processes, three phases in detail in the next session. So we will go through that. And as also I said that we'll go somewhat faster. Therefore, we will move faster in this lecture, so that we can cover that syllabus as enough syllabus within the stipulated time. So pre-processing is what? Pre-processing in CAE refers to preparation of data and models. This is very important wording here. What does it means? That first step is pre-processing is data cleaning. So data cleaning means what we are going to go. We will go for any errors, outliers, there are missing data that are identified. That all are identified and then that are corrected. So this is the first step. So most of the time this step is not required, as because most of the time we have fresh start, and in where we need to go for a model to be prepared or model to be created inside the access. So how to create that model? Model means shape and size of the object for which we are going to do analysis. So that object first seen, that object dimensions are first considered, and same as that of we draw it in the isometric projection. Similarly, that that we draw that object in the draft that object in the modeling software or in ANSYS, directly in ANSYS. In ANSYS also modeling is possible. And if very critical geometry is there, very critical shape is there, and so on, which is not possible, suppose in ANSYS, in such cases, we go for drawing that in some modeling software like Creo, CATIA, SolidWorks, Solid Edge, like that, even AutoCAD. So we draw that all in that modeling software, and then we import that file in ANSYS for further analysis, right? So then the model is then meshed and discretized. So what is meshed and discretized? So as I said that we are going to convert that all object into some nodes, some elements. So very small elements are made, and what type of mesh, how many type of element, how many type of nodes, and all. That is also very critical part. So we are going to mesh in our practical session. So you will see that. Then after meshing, when you go for meshing, automatically will discretize that object. Okay, discretize means you are just converting the object in small parts, which then after will be analyzed independently. The next step is the quality of mesh. As I said, we have to decide what is the quality of mesh that is to be used. So it depends on various parameters, and our unit 2, after this unit 2 is specialized on meshing only. So in that unit we will go for detail of meshing. Meshing means formation of nets, simple net formation on the surface and across the volume of the part, and then we go for analysis. Then the last step in the pre-processing part is boundary condition and material properties are assigned. So you go for assigning the material property. There is a toolbox that get pop up in the ANSYS. Mostly I talk on ANSYS software only. We are going to use that. I'm talking that again and again, ANSYS. So there are many softwares comes under CAE, and I shown the list also to you. But ANSYS is the one that we are going to use. So in ANSYS, that is there is one window that get pop up in which it demands for what is the material. It doesn't ask the name of the material actually. It asks for the value of modulus of elasticity in case of stress analysis and Poisson's ratio. So I think that you know what is modulus of elasticity and Poisson's ratio. If not known, then revise it again. You learn that in strength of material, solid mechanics subject. Name of the subject now is solid mechanics. So that two values actually you have to collect from the material. So you can collect that from the design data book, what material that you are going to use for that part. According to that, that value will be given. Sometimes modulus of rigidity is also asked if torsion, torque, twist is there. In such cases, it also asks for G value, modulus of rigidity. So in this way, these values you have to give, and there is one more selection that you have to do is shell selection, element selection. So that element actually indicate a solid body or hollow body or a simple beam of plate like that. So there is a material library that you have in the ANSYS, and because we are going to come across the student version only, therefore the material library will be less as compared with the industry version that is used in the industry. So industry also use ANSYS, and in that version it is paid version. I think there is a 2-3 lakh rupees must be there for one license. And the student version that we are using is free of cost. It is available as open source, and therefore it is having some feature less as compared. Feature less means the facilities will be less. Here we are having this version for learning that software only, and in company industry when you are going to actually work on that, if given to you, if your job profile is about ANSYS, use of ANSYS, then in that case it will come to know to you that how advantageous and facilities very high. Material library is full of the all materials that are generally used in mechanical engineering application. So anyway, we'll go for the second, that is we calling as solver. So solver phase is a critical step. So now here this solver step is explained in detail in this slide. Whereas in computer or during when you are going to use that in ANSYS, you'll find that just one click is a solver in the software. But what that computer is doing under that click, that is explained here in the slide. What it is going to do is solve the mathematical equation to predict the behavior of physical system. Right? So how it is going to solve? So numerical algorithm to solve the equation of the model created in the pre-processing stage. So some algorithm it use, some program it use. The program contains some formulae, and that formula already included during the program which is framed, and the calculation is then after done. It is using some shape functions. That shape functions are actually helping for solving that part for analysis related to some parameters. Now, what is shape function and all? That is our next topic that we are going to learn in next session, mostly next or next to next. And then it uses various numerical methods for solving this. So what are that numerical method? We've seen already that FEA, finite element analysis, finite difference method, or boundary element method. So these are the numerical methods that are used in ANSYS. Mostly finite element analysis is the method that is used. So FEA. So therefore, sometimes at the place of FEM, FEA word is also used. It is finite element analysis. So finite element analysis using finite element method, like that. So the solver phase can be a time consuming. It takes some time to come out with a solution. It depends on how complicated geometry that you have, how complicated meshing that it has, and how that element selection is done for the meshing. Again, element and its type is the next part that we are going to see in the next session. Meshing elements. So in that we will discuss for this. So depending on element, this solver takes time, and after some time it gives the solution to that analysis. Okay. So next step is parallel processing and high performance computing techniques are often used to speed up the solver phase. So these two things are going in an industry actually, ANSYS, because in the student version we don't have this to use, and we don't need to use this. In student version we have very simple geometry, very simple meshing, and suddenly within some minutes you get the solutions of the problem. So in industry, when there is very accurate values are required, high precision is required, in that case we need these two supportings for speeding up the solver phase. The output of solve phase includes results such as stress, strain distribution, displacement, velocity, acceleration, and temperature. Actually, stress, strain distribution and all is thereafter calculated. The direct output that we get is either displacement or temperature. In case of heat, temperature. In case of structural analysis, we get displacement. So going for the third step, that is post-processing, third phase. So in post-processing, analysis outcome is available at that time, we call that as a post-processing first step, right? So the post-processing includes the all data in the numerical form, and that data can be used for certain predictions. That data can be used for some conclusions, and that data can be used for validation of the software with the actual values. So this data actually can be in the form of contour plots, streamlines, and animations also. In case of vibrations, the outcome you can see that animated in the animated form where it is vibrating actually. So it shows the type of vibrations, type of actually it is called as modes, type of modes that you get after the analysis. And it also talk about the frequency of the vibration, its values, with how many frequencies it is going to, with how many natural frequencies it is going to vibrate, and what is the value of that and all. So as you don't know this subject, therefore you are going to learn this subject in final year. Don't worry. What is natural frequency? How many natural frequencies could be there, and so, and for on which parameter it depends. So then after, other post-processing techniques can include data extraction, okay, statistical analysis and optimization. So that data can be extracted through some export tabs, and that can be recorded in the computer folders, or you can take out from that for its further processing. The post-processing also involves comparing the simulated result with the real world data, that as I said, validation. So validating that data whatever received, that is important actually, because unless and until we validate, why to go for analysis if the data received is deviating from the actual, if the actual data is somewhat different and data what you are going to get as a post processing or as an outcome is different, then there is no need of this analysis. If the data is matching, then this analysis of any use. So therefore, validation is a very important process that is done. And in projects also, if you are going through some analysis project, in B project I am talking, or even in master's project. In master project, that is very important. In B project, it depends. In master's project, we need to validate our results. Whatever the project you have and what is the tested data that you have to validate it. And validation actually gives the confirmation. It gives the confirmation of your degree. Then after, your degree will be accepted. Simple. So going for the next. So this is about the tools that are used by CAE for its analysis. Now if I move for the next topic of our subject, and next topic is somewhat related to your exam point of view. So we have seen many steps that are included in pre-processing phase. There are many steps that are included in the post-processing phase, and many steps included in solver phase. So if it is been asked to me in the exam that write down the basic steps in FEA or basic steps in CAE, so that can be summarized like this. Or if I am using FEA as a method for solving, what are the steps that are followed? So that steps are here. First is discretization of body. I am just summarizing what we learn now from the 3 slides. And you just remember these 9 steps only. And these 9 steps you can list and you can elaborate if asked in exam. Simple. Then second, we know what is discretization of body. Therefore, I am not going through details of that. Formation of global load vector. Now, this global load vector and again some vector that coming in picture in the next steps, that will understand in detail. No worry about that. I'll show what is vector and how it is formed. Right? Load here is representing force. So global force vector, actually it is talking about. What is that? We'll see. Formation of global nodal displacement vector. So at the nodes, what is the displacement and what are the values? We form that vector. We are going to use matrices, okay, mathematical tool for forming these vectors. So just go for matrices again, learn the fundamental of matrices again. At least you go for solution of matrices, how you solve that, and inverse of matrices. These are the two important points you have to revise in case of matrice. So global nodal displacement vector will form at the third. Fourth will be formation of element stiffness matrix. So as I said, matrices we have to use. Element stiffness matrices will include all the values of stiffness at the nodes. So what is stiffness and what is the definition of that? It is related to spring. That you again revise it. I think you have a design of spring in your syllabus. In the last design of element or machine element or now dots design of mechanical system, transmission system. So in that you may have that springs as your syllabus. I don't remember 19 pattern. Where is that particular unit is now? So stiffness is related to that. Formation of global. After element we go for global stiffness matrix. Then formation of global stiffness nodal displacement and load equations. So actually these global load, then nodal displacement, then element stiffness, then global stiffness, and then global stiffness nodal displacement load equation. These are actually coming one after each. You will find one vector when received, multiplying it with some other, you are getting second and then third and then fourth, and we are reaching to the sixth. As I said, we are going to see these all in detail. Then seventh step is incorporation of a specified boundary conditions, right? So then after we will apply the boundary conditions, that which surface, which part, which node is fixed, which is free, and what is the force that are acting there. Are they point load? Are they uniformly distributed load? Are they uniformly varying load? Is there any couple that is acting? Is there any torque that is acting? Is there any moment that is in between? All that are to be assigned to that particular part. So that part actually is going to be used in some machine, and in that machine, what are the different forces, loads that are going to act on it, couples that are going to act on it. That all we have to assign in the NCs to that particular part which is made, which is drafted there, so that we can make it very real, nearer to the actual, and then we will go for the analysis. And the eighth is solution of the simultaneous equation. So that simultaneous equations are simultaneous equation means we have multiple equations together and we have to solve that simultaneously. A set of equations that are solved simultaneously, and matrices is the tool that is used for such simultaneous equations. So we must know the application of matrices. Then ninth step is computation of element strain and stress. So we get actually displacement as an outcome in FEA, and from the displacement we can calculate strain and we can calculate stress. what is the relation of displacement and strain, and strain and stress, that actually you just see. C means you just revise it again. So revision of strength of material. At the actually in the first lecture only I explained about prerequisites of this subject. Prerequisites means the subject you must know before learning this subject. So I talked about some of the subject which you must know, and at least if you don't know whole subject, at least the concept which we have from that subject here used again, that concept also, or that concept even if you know, that is enough. Going for the next step, as I said that basic steps in FEA, these all 9 steps, actually these all 9 steps we are going to follow for solving the numerical problems, numerical questions. So when actually we will form these load vectors, nodal displacement vector, element stiffness vector and all, you will understand that in detail. So after learning that, you just come here again for this slide and see these 9 steps. You will find that okay, you are understanding each and every step very easily after when you are going to use these vectors in actual with some values, with some problems given to you. Anyway, going for the next topic of our unit, and that is examples of various types of elements. So this is very important concept of the unit. And as I said that on the basis of these uh, elements, or on the basis of your decision for the elements, the analysis depends. How that analysis is going to be accurate, it depends on the selection of elements. So before going for selection of elements, we need to understand what are the different type of elements that we have. So these elements are available in ANSYS software, and you can see their name written, and you can click that particular tab to select that element for analysis, for meshing, for meshing. Next unit, as I said, is only meshing, especially for meshing. So in that we are going to see these elements, how it affects, how the selection of elements affect the geometry also and the analysis also, outcome, results, post processing, how it get affected due to type of elements. So there are basically 3 types. You can see here in the slide. We'll go through this slide, and thereafter I'll take the attendance and we'll stop for this. Because I think 340 or 350 is our lecture timing. No worry, we have time, enough time. We'll go for other slides also. There are 3 basic elements. So you just keep in mind, and I'll revise it again, that what is element is. Element is nothing but a small unit that you converted from the part which you are going to analyze for any particular parameter, like for stress, for temperature, for heat, for thermal, for fluid, or anything, modal vibrations. So that small part together with connected to each other will form a whole geometry, whole part, whole machine part. So that small part can be of 3 types. And what are that 3 types is, either it can be 1D element, or it can be 2D element, or it can be 3D element. Simple. So this D stands for dimensions. 1 dimensional, 2 dimensional, 3 dimensional. So you know what is one dimension, you know what is two dimension, and what is three dimension. One dimension is in one direction only. Two dimension means two directions. So if I take 1D, it is representing line. Whereas when I take 2D, it is actually surface or a plane. A plane is 2D. And 3D is volume. In 1D, we just have X or Y. Whereas either X or Y, 1D. But when we have 2D, we have X and Y together. There will be one axis, we call it as x-axis, and other y-axis, we call it as y direction, that we call as y-axis. Whereas in 3D, we have one more axis other than x and y, that we call as z axis or z axis. So in this way, the space will get created due to 3D. So when the 1D element is there, there is a name that we are going to use for 1D element, like spring, damper, beam, or truss. For these names or for these such cases, we will use 1D element. But if it is 2D element, we will use a shell or plain 2D name for that particular element. And for 3D element, there are two types. What we are calling is hexahedral and tetrahedral. Now, what is 1D, 2D, these names given, and 3D elements will look like? So, if you see the row of 1D element, in the third column, you will find that how it going to look like. It is one line and 2 points at the end. That 2 points actually represents nodes, and another element connected to it will be connected to this element through this node. So depending on the criticalness of analysis, we can use this 1D element in its first order or in its second order. So what is the difference in that? If I'm going to use it in a first order, then it is 2 nodes only. But where I want to use that in a second order, it is going to take 3 nodes. In one element, 3 nodes will be there. These are not 2 elements. This is a single element, but the number of nodes is 3. 2 node element or 3 node element. 2 node 1D element, 3 node 1D element. This is the nomenclature that can be used for these two. What is the advantage? Actually, just introduction of that advantage, I'll show that to you, that what is the advantage if I use 3 node instead of 2 node. So you will get a refined machine if I use second order element shell. Any 2D, 3D, 1D, if I use second order, the machine is refined and the analysis is very precise and accurate. The drawback is it takes time. Analysis, machine, solver is going to take more computational time compared with first order element. So this is the drawback actually. But if you are going to compromise for time, you can use this second order elements. If I go for 2D, there are 2. One you can see here, triangle, 3 nodes and 3 lines connected to it, or quadrilateral. This 4 is called as quadrilateral. This triangular can be of second order if I give one more node on these lines. So you can see that 3 node triangular element or 3 node triangular shell element or 6 nodes triangular shell element. Here we have 6 nodes. Same is here. Here you have 4, where here you have 8 nodes, if the quadrilateral element is second order. And if I go for the hexahedral, so it is 3D element. It is mostly used for volumes, representing the volumes. So in 3D, in hexahedral, you can have 8 nodes at 8 corners. But if I go for more nodes in the element, in the line, then you can see here 20 nodes. These are 20 nodes hexahedral 3D element. One more element that is used is tetrahedral. This is 3D element again. It is 4 node tetrahedral element. And if addition of node is been done here, then you can find here 10 nodes tetrahedral 3D elements. Even the comparison between 1D, 2D and 3D can be done, and comparison between first order 1D and second order 1D can be done. So these are the elements that we generally use. If you go for in some other book, you will find a list of elements and name and their different notations associated with that. So here I am just showing the image of the elements, their names, and actually some other things are also associated with that. That what are the degrees of freedom that it has, how many ways it can move, and therefore what is the parameter that we use for its motion. If it is 1D, if it is 2D, what is the difference? And if it is 3D, what is the difference? And so that we'll see. Okay, we will see. Therefore, you just remember the elements which we are going to use.